All right, so my name is Nick. I'm the last surviving member of our group of three. They're in LAX. So yeah, we're down sort of to a different regime now, where we're in the flagship class. So this was the Coronagraph flagship mission. We are 8 MAW, 8 meters of awesome. And so yeah, we really are in a different regime. You can go to the next slide, where really cost was no obstacle. We had $12 billion in for our budget, and we just cranked everything to the max, and we still came out under budget. So we have an 8 meter mirror that gives us an inner working angle of 28 milliarcseconds. We boosted our coronagraph to a raw contrast of 10 to the minus 10. We did a 5-year mission lifetime out at L2. We used the cheapest appropriate space launch vehicle, which was still some of the bigger ones. And we came in at $11.42 billion. So still a $500 million or more under budget. And this is definitely an Earth oriented mission. That's what we optimized for. And we got almost 16 Earth detections. So that comes out to about $0.7 billion per Earth. So if you're ever wondering what this scale balances to, it's $0.7 billion. And we would also, this survey is optimized for Earth, but we'd probably find all of the other brighter planets in the systems that fall within the field of view. We didn't run the numbers for optimized missions for Jupiter or anything like that. And the reason is that if you have this type of capability, it would probably be best, if you were interested in Jupiter's, to use the capabilities more as a characterization mission rather than a search mission if you were interested in those other planets. So that was sort of our reason. We were focused on the Earths. Obviously, we'd find a lot of other things along the way. Next slide, please. We did, for curiosity's sake, look at the yield versus telescope size. It makes a big difference. So 4, 6, and 8, these are all well under budget, of course, but we were just curious how well that money was being spent. So we go from 4 to 9 to 15.8 Earths as we scale the primary up. We also looked at how much it's worth to invest in a good coronagraph, as well as good PSF subtraction post-processing techniques. So if you look at this little table here, the 8, 9, and 10 is the raw contrast. On the left, we have a factor of 10, a factor of 1, and a factor of 100 in PSF subtraction, additional contrast. And so you can see that the contrast, your coronagraph does a lot. It's sort of the fiducial case where you have the standard factor of 10 in PSF subtraction. That adds, boosts from 10 to 15.8. So it's really worth it to get that extra factor of 10 in your raw coronagraph. Also, having good PSF subtraction helps as well. So if you look down the table, all those techniques we learned on Tuesday are worth several billions of dollars if you scale the cost per planet up with your yield. And you also, if you look diagonally in the table, you can see that, of course, post-processing is not as valuable as doing it with the coronagraph. So we have one more slide. We looked at the Zodi level. So for the 3 Zodi, which was the sort of the default value, we had our 15. If we only had 1 Zodi, if everything was like the solar system, we'd be up at 19 Earths. And then if you go 3 times higher to 9 Zodi, you're at 12 Earths, wrapped down to 12. And if you go by a factor of 10 up to 30 Zodi, that reduces it down to 8. So it's actually not a huge effect. It's less than linear. And the reason it's not a huge effect is that you can optimize your observing strategy to look for the nearby systems. And again, I think as we discussed, or someone else discussed, the Zodi background becomes a problem far away, where your planets are getting fainter, but your surface brightness background of your Zodi is roughly constant. And so Chris's code, I asked him about this, is smart enough that if you increase the Zodi level, the observing strategy changes and focuses more time on the nearby stars to overcome this problem as best as possible. So that's it. Questions?
Hi everyone. We our name is 3, even though you might notice there's 4 of us. We hopefully will answer that question if you have that question. On Monday we only had 4 as well, but a different 4. Anyway, this is our 5 people listed here, the 4 that are still here. Andrew couldn't make it. I'm Elizabeth Young. We have Erica Gonzalez, J.R. Delhomme, and Ewan Douglas. So our mission is called 3. That stands for the highly redundant, extremely expensive Exo-Earth Explorer. And we actually thought of a couple more E's at lunch, but we already submitted our presentation. So it was trying to go on the fact that on Monday we had a little difficulty with typing one number, and a lot of numbers came out. So that's kind of behind our name. That's why there's some extra E's. Yeah. We found it very easy to come up with a name, by the way. Just a lot of E's. Okay. Next slide. Thank you. So we have $12 billion. We thought, well, let's just pick the biggest equivalent thing ever. So we did. And then we were like, okay, maybe we should play around with some parameters and try some other things out. So we were looking at kind of the 6 to 8 meter telescope range and looking at the cost per Earth that you find. And then we saw from this, hey, maybe the 7.5 could actually be a little bit better for your money than the 8. So we should go for the 7.5. And then we're like, okay, we're done. It's Monday. We still got a week, or part of a week. So let's explore a little more. So we tried 4 meter. And we're like, whoa, 4 meter, cheap, efficient, great, we got to go with this. So we're thinking the 4 meter, under $4 billion. We've got a lot of money left over. You guys were wondering what to do with your millions. We've got billions left over. So we thought, well, great, because being graduate students and researchers, we need that money. So we thought we'd just give it all to us. And the community would accept that, of course. But we also had some other ideas, too.
So that's where we decided, let's try 3 4-meter telescopes. So we had this, I think Ewan started with the novel idea of 3 4-meter telescopes, and we all agreed, hey, why not? So we talked to Chris and Augie and said, can we do that? And they said, well, why don't you try running 1 4-meter telescope for 15 years, which is the equivalent of 3 4-meter telescopes for the mission lifetime. And we thought it would triple our result in Earths, and it doesn't. JR will tell you more about that. Our reasoning behind that, besides the fact that we had all this money left over, was that we could use 1 launch vehicle to place these telescopes, and we actually could fit 9 of these 4-meter telescopes on 1 launch vehicle. We found that out too. And we did not account for how the budget would be lessened by having to only develop the technology on 1 telescope that we're just making a triplet of. But we did account for the fact that we're using only 1 launch vehicle. Our other reasoning was that, heaven forbid, one of the reaction wheels fails, we have a backup. And if the optics don't work well on one, we have some twins for it to work with. So next slide.
So then we found our oops. The code has an input for inner working angle and diameter, and we were only varying diameter, and we were using the inner working angle of an 8-meter telescope on a 4-meter aperture. So we had a factor of 2 better inner working angle, and that's where we were getting all those cheap Earths from. So while there was a cost savings below 4 meters, it wasn't nearly as big as we had been saying. So next slide.
So here for the third time we have plotted the cost per Earth as function of the size of the telescopes for mission lifetime of 5 years. But this time we also had the free 4 meters telescope. And as you can see, the cost per F dramatically increase in this case. So it's because launching a 4-meter telescope, it's almost like it's cost 3 times launching one telescope. So it's not a good idea. So if we're launching only one 7.5-meter telescope, we can find 14 Earths and 175 Jupiters for only $10 billion.
So we scratched our 3 idea. And so we decided to go with 1. The E's are just implied. 1 non-redundant, extremely expensive exo-Earth explorer. So in this case, we use the 7.5 diameter telescope with the highest contrast we could use. Our inner working angle and outer working angle were just dependent on our diameter. For Earth, we were able to look at 372 stars, yielding roughly 14 Earths, or 13, and many more stars for Jupiter. We spent so much time on our OOPS that we didn't look at the Exozodi, but we do know that that is important. So these are our conclusions, and our final lesson learned was that the inner working angle is important. Thank you.
Okay, so we are the first of the flagship Starshade missions. We have the most literal name possible. Everything you need to know is in there. It's an Earth-finding, direct imaging Starshade mission. Start with the answer, because our primary science goal is to find number of Earths, so that's what we maximized for. Like the first Coronagraph group, we applied a go big or go home algorithm, and just made everything as big as we needed to get the number of Earths. We found 6.8, which is quite a bit less than the Coronagraph one, and we have a lot of reasons why we think that is. Next slide. So here's the mission parameters. If any of you guys want to talk, you just grab this from me, by the way. Okay. So we went straight to the 8-meter telescope. We weren't worried about, we thought a little bit about, planets per dollar, but we just tried to, max out the science goal. Mission lifetime was 5 years. We were also allowed to increase the science fraction 30%, so we did, and the bandwidth to 50%, so we did. We kept the number of exozodis to the default, and for contrast, BJ will explain a little bit why we made this choice, but we basically just kept it at the level where you need to find Earth and not trying to go any deeper, because that did affect our yield in the end. And our inner working angle, after trying to optimize that also, we ended up with 47 milliarc seconds. So next slide. So BJ's going to talk about his plots.
All right, so we tuned a few parameters here to see what would happen. The first thing we found, probably the most interesting, is that if you change the inner working angle and you make it smaller or bigger than this 0.47 number that we found, you actually lose Earths. Your yield decreases. And this is because you start to spend so much time slewing the Starshade, because it has to be farther away, that you just don't have the time. Next slide. And this actually illustrates that. So as your working angle decreases, you see that it increases the slew time, the total slew time of your Starshade, maxes out at the mission lifetime of 5 years there, saturates. All right, next slide. This is also true with the contrast limit. So if you actually expose deeper, if you're looking at fainter stuff, then the same situation applies. You have to have a bigger Starshade farther away, and you have to expose longer, so you start losing yield. So there's a peak, a maximum here too. Does someone else want to take the next steps?
So to go along with that, we kind of so in here you see our Starshade size gets set by the inner working angle and contrast. It's relatively small. The slew time is only about 14 days per target, and we're going to the maximum number of targets. So that's kind of where we were trying to optimize for, is finding Earths, but going to all the targets, and that's really what got us most Earths. Trying to go to deeper contrast or smaller inner working angle didn't really help because we were losing so much time when we were only going to 20 stars or something like that. So finding the most Earths, and I mean, it's beating a dead horse now, but doing a blind survey like this is not the best way because you really want to go to as many targets as possible or know that there are good targets there already. We're well within our launch margin. Our cost was just under 12 billion, like expected. Next slide. So we did also, kind of double check that checking different diameters made a difference. Obviously, they got cheaper, but we found less Earths. So just maxing out at the biggest one seemed to be the right idea. Next slide. So like I said, these were our important lessons that just naively trying to go closer in or deeper in contrast didn't actually get you anything once you ran out of the number of targets that you could go to. And then next slide. Oh, right. So for the secondary, we found about 1 Jupiter, about 2 Neptunes, and about 4 more mini Neptunes with this mission architecture. We tried playing around with the Exozodis a little bit and found that it was not a very steep function because I think we were limited by that we were already looking at all of our targets anyways. So we don't have a plot for that, but we did check it. So Tom is really good at coming up with acronyms.
When you're commuting back and forth from the west side of LA, you have time to think about these things. So we didn't know there was a prize for best acronym, but luckily we came up with a few extras. So either we're fearsome, so we scare the exoplanets out of hiding, or we are fearless and not afraid of budget constraints or timelines. Or kind of my favorite is Erebus, which is the Greek god of shadow and darkness. And we tried to sell this to Congress with as an extremely reasonable Earth finding by occulting Starshade mission, which is quite opposite from the the extremely expensive telescope that was before us. So I think if we put this in bold text and then the cost in fine print, we will outdo the other mission. I think that's all. We have one more.
All right. So.
Oh, right. Yeah. So with is this the extra cash for if we step down to a smaller, or any extra cash we happen to have over? Yeah. And we could spend it on. Possibly things like this.
So, preferably a logo that shows how we can have such a powerful yet sensitive instrument with a nice, beautiful flower-shaped starshade. We could, pay someone to design something generally with this idea. That's all.
Thank you.
Hi everyone, thanks for staying until the end. We thought about naming our mission ship for characterization of Earth with a starshade and telescope. We were quite proud of it, but obviously another team has already made the joke about the cost of the mission with priceless. So we finally chose to name our mission Flower, which with a nice logo. It's quite the same idea of the previous logo, but quite different. And Flower for flagship, occulter for new world exploration. And this is the quasi-complete team because some of us are already in their way to Las Vegas, but I will not tell their name. So next slide, please. So this is the parameters we used for the mission. We use a telescope diameter of 8 meters. The Starshade diameter is about 37 meters, a contrast of 2 times 10 to minus 11, sorry. An inner working angle of 0.05 milliarcsecond, and a mission lifetime of 5 years. So, next, please.
So, as Mary mentioned, the best parameters that optimize the number of exo-Earths detected involved the 8-meter class telescope and 38-meter class Starshade. So 8-meter class telescope is very heavy, about 10,000 kilograms. So this implied the choice of the biggest spacecraft to launch the telescope, spacecraft G. Then for a 5 years long mission and 825 kilograms Starshade, we had to choose spacecraft Z for the Starshade. And so with a total payload mass of more than 10,000 kilograms, we also had to choose the biggest launch vehicle, the launch vehicle F. So with all those luxury choices, we are still just under the budget limit. So we are good as long as we don't get budget cuts.
So this is showing our planet yields. Since we had a goal of finding Earths, we tried to maximize that. We have 7.4 Earths assuming an eta Earth of 1. The secondary goals of finding the other planets, we get a few of the other planets. We get about 1 Jupiter, 3 Neptunes, and 4 warm mini Neptunes. And you can see if you play with the eta, obviously the number of planets goes up if your eta goes up, just like expected. So if you want to work out that dollar per Earth number, it's roughly $1.7 billion for Earth if you want to use that. I think the answer depends on whether or not you're a taxpayer or a scientist, whether you think that's a good metric.
Can you go back one slide? So another thing interesting with this plot is that if you multiply the eta planets on the x-axis by the total number of stars in our sample, so 100 for the Starshade, the slope of this curve tell you the average completeness of the mission for the sample of star. So if you go one slide, please. So with this mission, we just achieve an average completeness of 74% for Earth, for a star-type planet, and 97% for Jupiter, 61% for Neptune, and 81% for mini Neptune, warm mini Neptune. So you can see that we are good at detecting every kind of planet, especially Jupiters and Neptune, but we are also quite good for Earth.
Next slide, please. So the goal of our mission is to find Earth, and we wanted to know how much the amount of exozodiacal dust will decrease our capability to find Earth. And we can see that for a few tenths of zodies, it doesn't really matter. We are still around 7 Earth detected, so it's still pretty good. But if we go to most extreme value, like 1,000 or 2,000 zodies, this is the value that can be found in nearby stars. We can see that it's really decreased the number of Earth. Like we are less than 3. So the exozodiacal dust is an important parameter to take into account in that kind of survey.
So in conclusion, did we forget a slide? So a chronograph might be better suited for other previous studies, as you found out, because they found way more planets. Next slide, I guess. Okay, so in conclusion, we found a complete niece of the exoplanet Earth, of about 0.74, which is quite complete for what you see, that's fairly complete for Jupiters and more mini Neptunes. And it will be really good, for the most part, with characterizing these various targets instead of just being a broad survey mission, which I believe everyone has kind of concluded the same. Let's see. Again, it doesn't necessarily use the majority of the time in the telescope, which will allow us to be compatible with other portions of the astronomy field. Thank you.
And Aki, but before we get that, let's try to sort of, having seen all of these excellent presentations, right? Can someone suggest what are the lessons? I mean, some of these we've heard already, right? I think several times, loud and clear. dependency on the benefit of doing pre-selection and things like that. But does anyone want to suggest something they learned about chronographs in this? We'll do chronographs first, then starshades. We have.
I know it's the end of a long week.
I know, it's the end.
A little bit, reach in there.
I thought one thing that was interesting, right, is to think about the strong dependence on diameter. If you compare across all the missions, not just a single mission, but the little probe class size versus the flagship scale chronograph, right? What drives you to the big ones, right? It's all about getting to the inner working angle, right? So that was I think is a key lesson, that if you're looking for Earths, I mean, we're driven towards this big flagship mission. But there is interesting science you can do at the small scale. And these these categories aren't arbitrary, right? They exactly parallel the real studies that are going on now, the XOC, XOS at the small scale, and then we're also working on the vision of something like an Atlas mission in the 2030s at the big scale. How about the trade-off between diameter and lifetime? I like that one early on. Right? There was who had that on their slides? It was one of the groups.
I don't think we had it on our slides, but it's something I did notice. Larger starshade could really limit how many stars you could see in just a 5-year mission.
Yeah, and all these missions, you're focused on sort of 5-year. You think about what about Hubble is 25 years old, right? Why didn't we let the lifetime of the parameter space extend out to 25 years? Starshade would run out of fuel. That's good. What about chronographs? Things break. That's certainly one possibility. Yep.
And Hubble, they got fixed.
Mm-hmm. Say again? Yeah. Well, and the other thing that happens, in some of these missions, you see that the dependence on time with the number of planets you find is not linear, right? You hit a point of diminishing returns, especially in the DRM code, where we already touched on this point about the exozodis. That if the exozodi is high, well, it just spends all the time preferential on the best stars. You're going to observe the best stars in the first couple of years of the mission, and so you can go arbitrarily long after that. And for these, you end up exhausting the sample. Once you start getting into a 16 or a 20 meter, if we're really ambitious, then the parameter space starts expanding into many hundreds of stars, and maybe you want to go longer. How about starshades? I think we've heard a couple key points on this already.
So I thought interesting, there wasn't that large a difference between spending 1/2 of 4 billion and 12 billion in the amount of Earths detected. That with 12 billion you saw maybe 6 Earths,
Mm-hmm.
with 4 billion you saw maybe 3 or 2 roughly. And this thing is really worth $8 billion to try and get those extra few exoplanets.
So we'll come back to that on the next slide. Hold that thought. But yes.
Well, one of the things we didn't necessarily look at was how well we managed to characterize them. Just
Yes.
because we only detected 3 more Earths doesn't mean we didn't learn more about all 6 of those Earths.
Yeah, so I'm just going to skip ahead to this. So absolutely. I mean, spectroscopy is a key part of this that we left out of this exercise. And that's where the big missions really end up coming into their own. It's not just doing photometry and seeing these things, but being able to characterize them at moderate spectral resolution. And this is where starshades are really going to shine.
And I thought Aki mentioned during the talk that the starshades tended to be less affected by wavelength than coronagraphs, and so that would be one place when you start characterizing them, that the starshades, while less efficient, would probably be able to do things like IFUs and stuff, where they would be more, they would be able to characterize the planets in like greater wavelength.
That's absolutely the case. And we've been focusing mostly on optical wavelength characterization, but there's a lot of interesting science in the near infrared as well. And some of the atmosphere scientists are now saying, we really want to get spectra of these planets at 1.6 microns, 2 microns. So what's going to happen if I say, do an exoplanet direct imaging mission at 2 microns? Right, how does that depend on, what's that going to affect on the design? The inner working angle will change, right. And so to do at 4 times the wavelength to get the same inner working angle, you either need to fly 4 times bigger a telescope, so you're launching a 32 meter, or you want to fly a starshade. Right? A starshade is the only plausible path to characterizing Earths at 2 microns, if you want to go that route. That's right.
coming into each channel. By some order of magnitude.
Yeah.
So is that are there infrared detectors that are feasible to do that kind of quality spectroscopy?
I think in the visible they're starting to get there. In the infrared, there's a way to go. And this is one of the things that people would be looking at for these sorts of missions. Detectors are key. So yeah, I mean, I think the spectroscopy is one of definitely the real strength with Starshades. And we've heard this point a bunch of times. Blind imaging is not what you're going to do with a Starshade. And there's a potential. Jeremy Kasdan has argued that why not, for your $12 billion, design we heard about launching 3 small spacecraft, right? Why don't you do a $8 billion Coronagraph mission and a Starshade with that as well? And so maybe the idea is that the Coronagraph does the survey and then the Starshade does the follow-up characterization with the much better spectral bandwidth. So that would be one possibility.
Yeah, so it seems like, to go even further, that a Starshade is a great add-on to a very multi-purpose mission. That you can support a lot of different science, and then also a Starshade.
Yes.
That will get a lot of people engaged.
Yes, and the Starshade was studied in great detail as an add-on for JWST, and there are a variety of reasons why that wasn't pursued, but it certainly, you could add on a Starshade to Webb and do great things. You could take a mission that's launched as a Coronagraph and put a Starshade on it later, and that would do very good things as well. I just want to go back to the slide that I skipped. That was about thinking back to the small scale for now, that the yields were pretty low for the small scale missions, right? The XOS level, $1.5 billion. And so, of course, we made this point that you're going to do pre-selection. And so, in reality, you can look at yields, at the 2 dozen level plausibly for these small missions. And I definitely invite everybody to go look at these reports that are online. You can read the reports of the studies right now and see how this is done in much more detail as we think about both the little side and then the big side. If you want to think about full-size missions, there was studies done for the decadal survey of ATLAST mission concept, studied a 8-meter, 9-meter, 16-meter possibility. And of course, the community has been studying these DRMs, design reference missions. There's one every couple of years, new set of designs. So we'll see what happens there. Are there any other thoughts on the way to fit these pieces together, or lessons learned, or final conclusions? Abby?
I think for the Starshade, one of the things that clearly comes out that nobody's actually going to spend $4 to $12 billion on an exoplanet mission alone. And the really nice thing about the Starshade is that the mission would essentially have the entire community doing their own science and invested in the telescope without, while also being able to do all the other the direct imaging kind of science.
I think it's extremely important that we get everybody on board with this mission. Very broad community.
But you can still have an 8-meter telescope with a coronagraph that has other instruments on it. You just don't have to spend.
And I want to make it clear we were only using 20%.
True, but that was also
the Starshade forces you into the mode where you have a large general purpose facility. The coronagraph, it's sort of it's not technically forced on you, but it's a reality that you build this facility. Just as Hubble was built to do the Hubble Distance Project and measure the expansion of the universe, and has done lots of other stuff. Just like Webb is being built to do the high Z universe and the first galaxies, and will do many other things, right? For JWST, we're all part of and it'll do some other stuff too, right?
They're one of 4 stated goals of the observatory.
Yes.
Exoplanets is one of 4 goals for JWST.
Yes.
Not an add-on.
It's not an add-on, but it is not what drove the design of the observatory. The observatory design, it wouldn't be at 40 Kelvin if we were doing exoplanets was the key primary driver.
5 microns, good stuff.
5 microns, good stuff. No, don't get me wrong, it's great. And similarly, for the extragalactic science, they may want things, that let's say it's an off-axis 8-meter, or it's a giant segmented telescope. These are pushing us in the direction where it's a beneficial design to large portions of the community. And so we can joke about it. This is a summer school; it's casual setting, but it's actually very serious to think about. We have at the town halls the joint meetings of the Exoplanet Advisory Group and the Cosmology Advisory Group, trying to sort out exactly how this can possibly play out. You had a comment on Aki's last slide, but yes.
So it says RV detected. It sounded like
But
Yes.
it seems like there's also an empty parameter space that transits and RV aren't looking at. So would you maybe want your probe to target the perpendicular plane where you're not as sensitive? So you would, if you're just looking for detection, don't look at systems where there's already a detector.
Well, again, the goal thinking about, say, for instance, characterization, right? For your probe scale mission, remember the probes were all focused at Jupiters. So that's a regime where the Earth's, where Earthbound RV observations can get you to see Jupiter. So you know they're there, and you go and you characterize the Jupiter. And yeah, you can do a blind survey and go find some Neptunes or something like that. That's part of the parameter space that's not as well explored. Was that your point, or did I misunderstand your question?
Just like would it be beneficial to skip stars that have already been looked at in RV?
Well, this goes back to the point of is the goal detection and counting and saying, hey, we found this dot, right? Or is the goal to go beyond that and get to the science, right? I think we've all heard the notion of Carl Sagan's statement about the Earth as a pale blue dot in space. I think we need to keep in our mind that the goal is not pale blue dots, it's pale blue spectra, right? I think I'll turn things over to Don.
Well, it'll be a very short number of minutes. I'm sorry I wasn't able to be here for the first part of the meeting. I was off observing on Mauna Kea, but it certainly sounds like the meeting went very, very well. And I think certainly the studies you guys were able to do, particularly given some of the hiccups at the beginning, at least in one of the rooms, I think everybody caught up and did a really fabulous job. So I just wanted to thank the people who did all the studies, the people who arranged the studies, Chris and Aki, who aren't here anymore, but Keith Warfield and Verteca, who did a great job. So 3 cheers for all the study groups and all the people who did that. And as Gary Blackwood said, you're all going to be drafted to work on all the various probes. And we certainly had some fabulous names. I like, 8 meters of awesome. And Quinn's statement yesterday, the best ever in the history of ever, is my new favorite phrase. One certainly liked parasol and flower, and Erebos for the classically mind. So we had some excellent names. Probably the only prize we can offer you is to invite you back next year with a free, we won't charge you a registration fee. But most importantly, what I wanted to do is ask all of you to thank the people who did all the work on the workshop, which are Dawn and Carolyn, Ellen, and all the other people from Nexa who just did such a fabulous job. So thanks to you guys. And we look forward to having you all back next year. If you want to write on the bottom of your survey form what you think the coolest topic for next year is, we'll start thinking about it over the next couple of months. And we look forward to having you all back next year. So thank you all for coming.